So in this problem, we're asking if this data set gives evidence that birth rates are not spread uniformly across the zodiac. And so let's work through it. Let's let P1 be the probability of being an Aries, and then P2 is a Taurus, so on and so forth. We'll go this way. We'll go this way. Whoops. Let me use my highlighter here. So Virgo would be P6, P7 would be Libra, 8, 9, 10, 11, 12. Okay. So we'll go down and we'll say P12 is the probability of the last one. All right, so the null hypothesis here is that everything is equally likely. So in this case, there's 12 options that are equally likely. So the null hypothesis is that P1 is 1/12, P2 is a 12th, all the way out to the last probability. They're all the 12th. And the alternative hypothesis is at least one piece of I is different or is not equal to a 12th. So that's step one. Step two, to be able to find the expected count, or to find the chi-squared statistic, I need the expected count. I'm not going to write out the table because they're all the same, so let's just note here that the expected count for each cell is just 1/12 because all the PI's are a 12th, right? So you're taking P1 times the total to get this expected count, and P2 times the total to get that expected count. But in this case, the total, were we given the total? We were not. You might want to add everything up. If you add all of these guys up, you're going to get 2,402. So I'm just adding up all of those guys to get the total. So the expected value, or the expected count for each cell, is 1/12 of that 2,402, which is 200.1, we'll just say 167. So that's the expected count. And now I can compute the chi-squared statistic. I won't write it all on the screen because it's a little bit tedious, but for the first one, for Aries, we would have 205 minus 200.167. It's observed minus expected squared, divide by expected, and then you go to the next one and you just add them up. So the last one here would be 198 minus 200.167. Square that difference, divide by 200.167, and when you add all those up, you should get out about 18.34. For step 3, we want our p-value. That's the probability that chi-squared with 11 degrees of freedom. Remember, this is, don't think that there's 2 rows. There is 2 rows, but this is not a test for independence data. This is a goodness of fit data, and so it's just the number of options, if you will, the number of categories minus 1. So there's 12 options here. The only reason they're in 2 rows was because it wouldn't fit on the page. So 12 options minus 1 is 11 degrees of freedom. Greater than, for chi-squared, it's always greater than 1834. And you're going to plug that in the app. You should get out 0.07402. And so we're going to say, for conclusion, that the data is not statistically significant. It does not give evidence that we're going to have a double negative here. It does not give evidence that births are not equally distributed. In other words, we were assuming, our null hypothesis was that births are equally distributed. We're going to fail to reject the null hypothesis. Our null hypothesis is that births are equally distributed, and this data did nothing to challenge that assumption, so we just keep on assuming that.